We'll see that measurements of submicroscopic events, those in the atomic domain, follow different rules than measurements of macroscopic events, those of our familiar everyday world. The uncertainty of measurement in the atomic domain, which was first stated mathematically by the German physicist Werner Heisenberg, is called the uncertainty principle. It is a fundamental principle in quantum mechanics. Heisenberg found that when the uncertainties in the measurement of momentum and position for a particle are multiplied together, the product must be equal to or greater than Planck's constant h divided by 2 pi, which is represented with a symbol h with a bar through it called h bar. My buddy Ken Ford, a prominent quantum physicist, sports h bar on his auto number plate. H bar is as central to quantum physics as the universal gravitational constant g is to gravity. The uncertainty principle can be stated in a simple formula. Delta P times delta X is equal to or greater than H bar. The delta here means uncertainty of. Delta P is the uncertainty of momentum. The symbol for momentum is conventionally P. And delta X is the uncertainty of position. The product of these two uncertainties must be equal to or greater than the size of H bar. For minimum uncertainties, the product will equal H bar. The product of larger uncertainties will be greater than H bar. But in no case can the product of the uncertainties be less than H bar. The significance of the uncertainty principle is that even in the best of conditions, the lower limit of uncertainty is H bar. This means that if we wish to know the momentum of an electron with great accuracy, that's a small delta p, the corresponding uncertainty in position will be large. Or if we wish to know the position with great accuracy, small delta x, the corresponding uncertainty in momentum will be large. The sharper one of these quantities is, the less sharp is the other. So, as a matter of principle, no investigator can know the simultaneous momentum and position of any particle with certainty. That's as basic to quantum physics as Newton's laws are to classical physics. That's the way it is. The uncertainty principle operates similarly with energy and time. We cannot measure a particle's energy with complete precision in an infinitely short span of time. The uncertainty in our knowledge of energy, delta E, and the duration taken to measure the energy, delta T, are related by this expression. Delta E times delta T is equal or greater than H bar. We have discussed before that you can never change only one thing. Every equation reminds us of this. You can't change a term on one side without affecting the other side. The uncertainty principle goes further. You can't even measure momentum and position or energy and time both to a high accuracy at the same time. Again, that's the way it is. And for emphasis, the uncertainty principle is relevant only to quantum phenomena. This is brushed aside by some people who apply the uncertainty principle to areas outside of quantum physics. A science buff friend of many years ago contended that if you stare at a person's back, the person will sooner or later turn around to see who is looking. Of course, he never put this to a simple experiment that anyone could do, but he liked talking about it and even wrote about it. I challenged him on his assertion, but he didn't want to hear about it and insisted that observing anything changes it, even in a small way. Here's where I, for one, am careful in defining what is meant by observing. If our observation involves probing, giving or extracting energy, we indeed do change to some degree that which we observe. For example, if we shine a light source onto the person's back, our observation consists of probing, which, however slight, physically interacts with atoms on his back. If he senses this, he may turn around. But simply staring intently at his back is observing in the passive sense. Whether you stare, squint, or cover your eyes completely, you in no physical way interact with and alter the atomic configuration on his back. Shining a light or otherwise probing something is not the same thing as passively observing something. In my view, a failure to make the simple distinction between probing and passive observation is at the root of much nonsense that is said to be supported by quantum physics. Better support for my friend's claim would be positive results from a simple and practical test, rather than the assertion that it rides on the hard-earned reputation of quantum physics. Some people conclude from statements about the interaction between the observer and the observed that the universe does not exist out there, independent of all acts of observation, and that reality is created by the observer. Others interpret the uncertainty principle as nature's shield of forbidden secrets. Some critics of science use the uncertainty principle as evidence that science itself is unreliable. The reality of the universe, whether observed or not, nature's secrets, and the uncertainties of science have very little to do with Heisenberg's uncertainty principle. The profoundness of the uncertainty principle has to do with the unavoidable interaction between nature at the atomic level and the means by which we interact with it. As a disclaimer, I must say that not all serious scientists hold that the distinction between observing and probing is relevant. Some scientists hold that any interaction between an observer and the observed becomes entangled, which would mean that even the moon in some small way is altered when you look at it. That's a part of the quantum story that goes beyond my imagination. I simply can't stretch that far. I want to leave you with a question. Consider making measurements of 3 moving objects. In which of the following are quantum uncertainties significant? Measuring simultaneously the velocity and position of a fast-moving A, golf ball, B, housefly, C, electron. Until next time, good quantum.